Hi everyone, welcome back to my channel Techvangelists. And if you are joining this channel for the first time, I want to say welcome. And if you're a returning subscriber, thank you very much because you mean a lot to me. You're so dear to me. Thank you for subscribing. And those that have not subscribed, it's your opportunity to do so because why not? You watch my videos, that's the only way to support me. Please smash the subscribe button right now and let's get started. Also, you can click the bell beside it so that you get notified when I post a new video. As you've seen already from the title, this is about fine-tuning large language models using the MLX framework. The MLX framework is an open source array-based machine learning framework developed by Apple. It is designed for efficient and flexible machine learning research on Apple Silicon. So I'm using an Apple Silicon machine, and if you are like me using the same type, the M1s, the M2s, M3s, the M4s, and I think M5 is at the corner, then you want to leverage this MLX framework for machine learning because it's much faster than the regular ones that you use like PyTorch. It's more like a combination of PyTorch and Keras together with TensorFlow, and Apple has found a way to just make the mixture and prepare something and cook it and produce what we call MLX. The core purpose is to leverage the unique unified memory architecture that the Apple Silicon uses, where the CPU and the GPU share the same memory in order to eliminate the need for the costly data copies between the devices, because normally for the other devices, some copies need to be done between the CPU and the GPU, and the data is copied back and forth as it moves for the machine to learn and for the model to learn during the process of training, which is a common bottleneck in traditional machine learning workflows. So it's built from the ground up to maximize performance on the Apple M series. And if you're familiar already with low-level Python APIs that closely resembles NumPy, if you're familiar with NumPy for array manipulation, and then you will find MLX very easy to use. It also provides tools for function transformations like automatic differentiation, which is essential for training neural networks and compilation. So let's look at it right now on how to install. So if you're like me and you've installed pip, I expect that you know what pip is. But if you don't know, pip is a package manager, a Python package manager that helps you to install packages. As simple as that. So pip install just like you do npm install if you're coming from the JavaScript world. For Python, you just simply do pip install MLX LM, just like that. And if you do that, then you're good to go. It's advisable to install this globally on your system, and then you can use it. So I've put this code together. Remember that what we're talking about today is about fine-tuning. So I've put this code together, and we need to just, first of all, when we talk about fine-tuning, what is fine-tuning? Fine-tuning a large language model is a process of taking a pre-trained LLM and training it further on a smaller specific dataset to adapt it for a specific task or domain. Think of it like taking a well-educated generalist, the pre-trained model in this case, and sending them to a specialized master's program. That's it. And then you have a specialized model after that. So from a general model to a specified model, to a specialized model, so to say. And that's the essence of fine-tuning. So for example, I have a model that is very vast in a lot of information, but I want it to be very good. Let's say it's got 30% on coding, it's got 20% on education, it's got 15% on law, different domains with different topics. But then I want it to be 80% vast on technology, for example. I would then take a technology dataset and fine-tune this model on top of that dataset so that eventually the model now knows 80%. So 80% of its knowledge base would be on technology, and the rest 20% will be shared amongst the rest of the domains. And this is essentially what the fine-tuning does. And what really happens in this fine-tuning, the model's internal parameters, which we call weights, are slightly adjusted using the new data. and this is exactly what we are going to see here. I'll be showing you that they what we call adapters. They are slightly adjusted, and the process refines the existing knowledge, enabling the model to learn the specific nuances, the terminology, and the patterns of the new domain. That's it. So Apple MLX has made this really simple, and we are going to be using what we call LoRa. LoRa stands for low rank adaptation. It's a highly effective and popular parameter efficient fine-tuning technique used to adapt large pre-trained models like large language models to a specific task or domain with minimal computational cost. So normally the cost that it will require to fine-tune this model would have been so huge. So think of the fact that you need a lot of GPUs, but LoRa makes it really simple. So the idea behind it is the discovery that the necessary changes and the updates, remember that I talked about that the weights of the model will be updated based on the new data set. That update to an LLM's vast number of weights during the fine-tuning can be effectively captured by a smaller set of parameters. And this is essentially what LoRa is. I will not bore you with all the details of LoRa right now because we just want to talk about the process of fine-tuning using the MLX. And maybe you've thought that this process was really difficult. Thanks to MLX from Apple, this process is really easy right now. I also must say that there are other fine-tuning libraries like Onslaught, but yeah, we are using MLX because we are using the Apple Silicon, and this is faster. So the parameters you need to pass when you're fine-tuning any model are this: Python, this MLX LM LoRa. So you will normally pass this way in your terminal. You will write Python MLX LM, and this is underscore, and then LoRa, and you start passing the parameters like that: train and model, and so on and so forth. So model equals to that, and data equals to that. So I've put all this in a command form so that we can just run it straight away. We don't have to type everything in the terminal. That's a little bit tedious. So now let me explain what this is doing. So I've taken this model called Gemma 3 1 billion parameter. It's a 1 billion parameter model from Hugging Face, and you can also do the same, or you can increase this. We have different variations of this model. You have the 4 billion parameter model. I think you have the 12 billion as well, but I've decided to just take this so that the process run is faster, and the data is coming from this calculator data. Now let me show you what this calculator data is. MLX requires you to put your data in this form: test, train, and valid. So test.jsonl, train.jsonl, and valid.jsonl. Now JSONL is just a format like JSON, but a longer string format. That's all. So it puts it in this format where you pass the prompt, the completion, and the reason why doing this is because of the type of model that we are using. So this model called Gemma 3 has a model card. If you go to Hugging Face, you will see that the model card looks something like that, where you then where you have this prompt, completion, and all that. So I needed to structure this calculator data in this way. So what we are doing here right now is that normally you would discover that this model, and we will test it very soon, it's already fine-tuned. So I'm not going to go through the process of fine-tuning this right now. You will see that it's already fine-tuned, because normally if you ask this model, is 25 bigger than 30, yeah, it should respond with a generalized answer. And sometimes we know that LLMs are not very mathematically accurate, so they can hallucinate when it comes to numbers. So this would then help us to streamline this LLM to a particular format that we need it to be every time a question that involves mathematics is asked. And so the same for the trained data set, and the same for the validation data set. So this is just to validate the training, and this one finally is to test it. So they all look the same, except that we've done it in a ratio. Let me see, this is 1, 2, so I have 99 rows here for the train. I have 12 rows for the test. I also have 12 for the validation. So this is a standard thing that you would normally do. The training data set must be much bigger than the test and validation. Usually the test can be a little bit more than the valid, but this time I've decided to just keep it the same. So let's go back here again. So we passed the model, we passed the data, and again, that's the folder of that data that must have the test train validation.jsnl. The batch size, these are critical parameters that you can play with, you can experiment with. In my case, 2 was okay because of the type of system I have. So I have a 16 gig MacBook Pro, and the batch size of 2 was just enough. I discovered that when I increased it, it was taking a longer time and it was not training. The iteration was, I've set iteration here to be 300 per epoch, and an epoch is, instead of epoch this time around, you can also set iteration, which means that the number of times it takes the model to go through the data set and learn. So it will go through this data set 300 times and it will learn. And eventually the adapter part is adapters, and this is the adapter. So we just create the folder here. Initially there was nothing in this folder. The folder will be empty. If you create this folder and you pass it here, you tell the model during the training, those additional layers that have been fine-tuned should be stored on this folder or in this folder, and eventually they'll be given something like this. So you can see the config and what happened during the training, save for every day's test, whatever, and you have the save tensors. This one will not open definitely. And you have grad checkpoints. Learning rate is 0.001. You can also adjust this. These are adjustable parameters that you can test out. And the number of layers is 8. You can reduce the numbers of the layer depending on your ability to run this. So if we run this command, this will go through this process. I will just show you, but I will not wait for that to finish. I will just run python.main here and let it start training. Let me just open a new tab, a new terminal here. Now we can test the model. We can test this model for sure. First, I want to test this model as its base form. Now, base form means that I've not added the adapters to it. After your training, if you want to test your model, if it has truly learned something from your dataset, so first of all, you need to LLM.generate, which will generate some tokens. It's like your chart completion. You pass the model, which is the model path, the prompt, which is this prompt. Yes, it's a mathematical prompt. The maximum tokens is maximum tokens, which in this case is 200. So if there is an adapter part, I then say add the adapter part, which means that we are adding the extra layers that have been fine-tuned on the model for this model to run. So we print the base model output. So we generate with base model plus adapters if there's an adapter path. Else we generate the base model only. That's the response from the base model with this same prompt. So I'm sending this prompt twice. The first time I'm sending it with the adapters, with the fine-tuned layers, and the second time with the base, which is without the adapter part. And if that happens, you get the result for the both of them. Now let's test this model. So test model, we use this one. The first time we run it with no adapter part, and the second time we run it with the adapters on the checkpoint. So let's see how this one is doing. Okay, it has started training, and you can see that first it loads the data set, it starts the training, it starts to iterate 300 times, and let's see if we can finish that even before the, oh, it actually finished. So that was really good. And you can see the peak memory was around 2 gig. So it just took around 2 gig of my RAM, which is 16 gig thereabout. And this was saved to the adapters as you would see it here. So now let's test this model. So we run the Python test, Python test. underscore model.py, and see it's just basically running that command in our command prompt. And the prompt is, would you say 0.1 is bigger than 0.11? The maximum token is 200. First response, it says yes, 0.1 is bigger than 0.11. This is without fine-tuning this model. It's a classic example of how we often perceive size, blah, blah, blah. Now, let's look at the other one with the adapters. Look at the response, very concise. This is exactly what we want it to be. Why? Because we fine-tuned it on this kind of responses. Now look at the response. Calculator, blah, 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 close tag calculator. And we specified it like that for every single one of them, And this is the training data. Yeah. Same training data. That's, so I need 1, 3, 4 plus 5, 6, 7, 8. That's calculator, this. And let's see, calculator, that. So it has seen this kind of message before. Where is that message? Something like this. Would you say that, let's find a similar message like that. Would you say, okay, look at this. That's one and that's another one. Would you say 999 is bigger than this? And in the response, it just returns calculator is this bigger than that minimum of this. Same thing for this one. It said I would say that. In this case, it gave us the response as this. So now we can then look for these tags. If we are processing the response of this model, we can then look for these tags and perform the operations by ourselves. And that ensures that the model gets the response correctly. So there will be no hallucinations when it comes to model. So what we've done right now is that we fine-tuned a small model to respond in a certain way that we can then take the response, do the calculation by ourselves, and ensure that this model never, or our responses is never hallucinated. I hope that makes sense. I hope you've learned something from this video. If you want me to share this code, leave a comment in the comment section and type fine-tune. Just comment fine-tune in the comment section. I will post this code on GitHub for you to download, and you can also play with. All right, that'll be all for this video. If you did enjoy it, please leave a like. Please share this video with your friends and every other person that you think would require it or want to learn something about fine-tuning using the MLX framework. Until the next one, keep learning, guys.